Hi everyone, and welcome to video number 8 of this series. In the previous video, I had finished with the discussion of the Josephson Junction, and from this video onwards, I'm going to talk about various qubit architectures. So, starting from this video, I'm going to talk about the charge qubit, which is also known as the Cooper pair box. And actually, Cooper pair box is the correct name, and charge qubit is just what people call it for short. So now the question is, what exactly is the charge qubit? So it is actually an LC circuit where both the inductance and the capacitance are provided by the Josephson junction itself. Also, the charge qubit circuit contains an additional capacitor CG. And this capacitor CG is also called the gate capacitor. Now, if I draw the circuit figure here, this is what the circuit of a charge qubit looks like. And the voltage source VG, this is known as the gate voltage. And I have already mentioned that this capacitor CJ is called the gate capacitor. Now, as shown in the figure, I'll assume that there is a voltage V across this capacitor C, and there is the voltage Vg minus V, which is across the capacitor Cg. Now, if we were to write the energy stored in the capacitors, it would be as follows. And I'm going to introduce the abbreviation. That is, I'm going to call C sigma as C plus Cg. And if I now rewrite the energy stored in both the capacitors, I get the following expression. Next, I want you to consider the expression that is given by half times C sigma, and we have this quantity that is V minus Cg over C sigma times Vg and the square of this. Now, if you compare these two quantities, that is the total energy of the total energy that is stored in both capacitors and this expression, you will see that the only term that differs is this term. And this expression would have something like Cg over C sigma squared and this square of Vg2. And if you compare these expressions, they only differ by a constant. And this constant is just the difference of these two terms. So the the constant by which these two expressions differ is given as follows. And if you are wondering why I am introducing this second expression here, it will become clear very soon, because what I'm going to do is, instead of using the expression for the total energy of both capacitors, which seems to be a little inconvenient, because it would be better if this term had a square as well. I'm going to use this term instead. And the reason is I'm going to use it in the Hamiltonian, which will be coming up soon. So uh, you'll see that if I change the Hamiltonian by a constant energy, it doesn't change the nature of the quantum system. So all of this is coming very soon. So I'll mention it again once we get there. Next, I'll introduce the magnetic flux. Now we have to find the magnetic flux in this way. And next, what we define is the flux quantum. which is nothing but h bar over 2e. And if you are wondering why this is known as the flux quantum, I will pull your attention to video number 4, where I wrote the flux of a superconducting ring, and it turned out to be actually 2n pi times h bar over q, where q was just equal to 2e. So if you now look at this expression carefully, this is just n times h over 2e. And you can ignore the 2 pi for now because this is just a multiplicative constant. So this is the integer and an integral multiple of h bar over 2e. So we can call this quantity h bar over 2e as a kind of a flux quantum. And so from the above two expressions, I can write the phase difference as phi over phi naught. And from the second Josephson junction, what we get is the voltage is just the time derivative of the flux. Now, next, what we are going to do is we are going to write the Lagrangian of the system. And if you don't know what a Lagrangian is, so a Lagrangian is basically the kinetic energy minus the potential energy of a system. So this is just the kinetic energy minus the potential energy. And from the previous video, if you recall, we had written the energy of the entire circuit, including the voltage source. We had written it as E naught times 1 minus cos of delta plus E naught over 2 omega p square times the square of the time derivative of delta. And if you recall, we had called this as the kinetic energy and this as the potential energy of the system. And if you also recall, the kinetic energy term was related to the energy stored in the capacitor. So in a similar way, we are going to write the Lagrangian of the charge qubit, which we have here. And doing that, I'm going to get. Now, you may notice that there are a few differences in how you would have expected me to write the Lagrangian. So the kinetic energy is the energy that is stored in the capacitor. Now, this is not the exact expression of the energy stored in the capacitor. But now remember that previously I had said that I am going to use this expression for the total energy that is stored in the capacitor. And you're going to shortly see why this is a more convenient expression and why it will make no difference to our future analysis. Also, coming to the potential energy term, so you would be expecting that there would be a minus E naught term as well in the Lagrangian. But again, so these are all just energy expressions and E naught is a constant. So even if we were to remove this E naught from the Lagrangian, it would make no difference to our analysis. And this is the reason why we pick this expression in particular, because this will make things easier for us in the future. Now, next, I'm going to write the canonical momentum. That is, I'm going to denote it by uppercase P. And this is just the time derivative of the Lagrangian with respect to the flux, the rate of change of flux actually. And so if we take the time derivative of, I'm sorry, not the time derivative, the derivative with respect to the rate of change of flux of the Lagrangian here, what we are going to get is the following expression. Now I have actually simplified the expression of the canonical momentum. and this is what we get. So we can think of it as a charge, that is CV, minus the charge CG times VG minus V. And if you actually recall, CV is the charge on the capacitor C, and so V is the voltage across the capacitor C, and VG minus V is the voltage across the capacitor CG, that is the gate capacitor. And if you recall the circuit diagram which I had drawn here, so and if we take the difference of these two charges, Q minus QG, this is actually so Q minus QG is called the charge on the island. So if you ask what exactly is this island, so the island is um, the region between the Josephson Junction, that is this one, and the capacitor CG. So if we take the charge difference, so Q minus QG is actually the charge on the island, and the way we define the island uh, is through these dotted lines. So we take this as the island. And actually, this charge is carried by a discrete number of Cooper pairs. And so we can introduce a new variable. So we introduce this variable n, which is the canonical momentum divided by 2e. And this actually directly corresponds to the number of Cooper pairs on the island. And now the Hamiltonian of our system can be written as p times the time derivative of the flux minus the Lagrangian. And if we substitute the value of phi from the previous page, I'm going to write it in terms of the canonical momentum. And if we substitute this value in the Hamiltonian, we are going to get the following expression. Now I'm going to add and subtract a term, that is CG square times VG square inside this bracket, and that will allow us to write the square of a quantity. It will help us to complete the square. And if you look at this expression, we can ignore the last term because this is just a constant. And if we add a constant to the Hamiltonian, it will not change the system in any way because that is just a constant energy. So we will drop this term from the Hamiltonian. Also from the first term, that is this one, if we pull out 4e square, so what I mean is if we take 4e square common from the first term, this is what we get. And we are going to define two quantities now. And so the first quantity is Ng, that is minus Cg Vg over 2e. And we are going to define Ec, that is 2e square over c sigma. And thus our Hamiltonian becomes simply as follows. Now, from our notation, it might be a little bit confusing that Ng is the charge on the gate capacitor, but that is not actually true. So let me redraw the circuit diagram here for you. So as you can see, the voltage across the gate capacitor is Vg minus V and not just simply Vg. So Ng does not correspond to the charge on the gate capacitor. So you might be wondering, like I mentioned in the beginning of this video, that there is this additional capacitor Cg, but you might be wondering that why do we need this additional capacitor Cg at all? And this is what I'm going to explain next. Now, to answer this question, I want you to consider a capacitor which carries a charge Q naught, and we will call this charge the offset charge. And this charge is actually caused by impurities during fabrication. So we are fabricating a charge qubit, and it is actually a circuit. So during fabrication, there can be an offset charge on the capacitor. And also, we are going to denote the charge that is added to the capacitor later by an external source, let's say a voltage source. We are going to denote it as Q of t, which indicates that this charge varies with time. So the total charge on this capacitor time t can be given by the following expression. And here the current flowing through the capacitor, this is uppercase I, and this is actually just so Q of t is just the integral of this current with respect to time. And so I can write the voltage across the capacitor at time t, and I'm going to denote it as U of t, and this is just Q of t plus Q naught, that is the total charge divided by the capacitance C. And so the energy stored in the capacitor can also be determined. And I'm going to assume that the charge on the capacitor, that is the external charge, at time equals minus infinity, this charge is zero. And so I can write the energy simply as follows. And so what this expression says is that the energy that is added to the capacitor by the external voltage source is this expression. I'm sorry, there should be a Q naught here instead of just Q. And the reason we got this expression was that the charge Q naught was already there on the capacitor. So the voltage source or the external power source which we are using, that did not place that charge here. So that is why we are getting this expression. Now further, uh, I can actually ignore this term because this is just a constant, and we can actually just write the total electrostatic energy of a capacitor. And if you have guessed it, that is just the total charge on the capacitor, the square of that divided by 2 times C. Now I want you to compare this expression with this, the one which we got from the Hamiltonian. And if you actually think about it, the the term Ng, it is actually controlled by the voltage source Vg. And so we can control this term if we change the voltage source, that is Vg. And so Ng can be tuned to compensate for the so-called impurity charge. And if you ask why this is necessary, so why do we need to compensate for the impurity charge at all? It could be very tiny as well. So actually, this turns out to be quite necessary because the number of Cooper pairs on the island can be easily outnumbered by the charges from the impurities. So remember that we are talking about a quantum system, and it is highly susceptible to noise. So the number of Cooper pairs on the island that we want to control, that can be easily outnumbered by the charges from the impurities. And so the behavior of the circuit will be dominated by random impurities, which is something that we do not want. It is highly undesirable.